Okay, so let's think back to Math 1, where we were solving systems of linear equations, and the solution to a system of linear equations is the point of intersection. But there are three types of solutions. The number of solutions to a linear system can vary. So we are also going to be doing three methods today for solving for the system. We're going to do graphing, substitution, and elimination methods, just as a review from Math 1. So remember that there's three different ways that a system can turn out. So the first way is when you have two lines with different slopes. And so go ahead and draw this in. You've got this line, for example, and this line, for example, and these two lines intersect at exactly one place. So we call this having one solution or one point of intersection. But I want you to imagine that there were two lines and that they never touched. And these are two parallel lines and they never touch. So there is no solution to this system because they never touch. There is no point of intersection. And finally, every once in a while we do a graph where the line turns out right on top of itself. Literally, it's the same line. And this is called infinite many solutions because they literally touch everywhere. So remember that if you get a system that has an x, y coordinate pair, it is a one solution system. If you get a system that says 0 equals some number, which is not true, it means they never touch. This statement is not true. They never touch. And if you get a system where you get some number equals some number, then that is always true. Then it is an infinite many solution system. These are just quick reviews on how to do these in case you need to remember the steps. Let's go down and actually do some solving systems by graphing. And also I just wanted to give you a quick reminder on how to check your answers for these. You're going to take the x value that's your answer and the y value that's your answer, and you're going to test it into both equations. So for example, the first equation is y equals x minus 5. We're going to test out the x value here, the y value here, and then solve both sides and see if they're equal. If they are equal, it is the solution to that line. And now let's just double check the other one to be sure that it's a solution to both. It has to be a solution to both to be a solution to the system. Since -1 equals -1 again, check. If the point works in both equations and you're able to check it, then it is the solution to your system. If it works in only one but not the other, it is not the solution to your system. So always check your work to double check that the point you got works. So for this one right here, up 2, and then up 1 over 4 and down 1 back 4, you've got this nice shallow line of graphing your first line. Then your second line is down 5, and then down 3 over 2 or up 3 back 2. And you've got this nice line. So we're expecting that from Math 1, you're able to remember to use the M and the B to graph easily in slope-intercept form. And then that point where they touch, in this case it happens to be at -4, 1. Feel free to do your work and double check that that's the point that you're getting. In this one, they're not quite in slope-intercept form and ready to go. The second one needs to be moved. So if I subtract 3 x's from both sides, I then get this into slope-intercept form, and now it's ready for me to graph. The other one was originally ready. So again, I go down 8 and up 1 over 2. Nice shallow line way down here. And then I begin at 6 and go down 3 over 1. And this one should be touching about right here if you're graphing on a nice grid. So excuse my little dots that were just over too much. And then this point of intersection down here comes out to 4, -6, if you've done this correctly. So graphing the first one, your point of intersection was 4, -4, 1, and the second one was 4, -6. Hopefully you remember how to graph these and find the point of intersection. On the next page, we're practicing the method of substitution. We're going to want to use substitution when you have a variable that's already isolated. Here we have the y that's isolated. Here we have the x that's isolated. So I'm going to get the second equation ready by rewriting it as exactly as it is with a big open parentheses for the y, because y is equal to -2x. So I can plug that in. Then we distribute. We combine like terms. And all this work just gets us an x value. We now need to take that x value, plug it back into either of the original equations in order to solve for the other variable. So technically substitution should be called substituting twice, because we essentially have to substitute twice to get both parts of the answer. All right, so the second one has a little bit bigger equation that's being plugged into the other. This time I'm leaving the big open parentheses at the beginning for the x. Because as x is equal to all of this, you can plug in the 4 minus y minus 1 there. We're going to combine like terms. All this work gave me one answer of y equals 1. I now take this and plug it back in. And my final answer is 3, 1. That is my point of intersection. This is the method called substitution, where you take one equation that's already isolated, you plug it back into another. The last method we're going to review is elimination. In this one, we're hoping for opposites, where in number 6, we're already given those opposites. For example, if we have that 3y and -3y are directly above each other, we can go ahead and eliminate those by crossing them out. So in this case, when we look at this one, we see that 2y and -2y are already opposites, and those will eliminate to 0. So we're going to add both rows together. Cross out the 2 and the -2, add the 3 plus -6, and the 4 plus the 2. Now that we got one answer, we take this and plug back into the other. You can use either equation for this. And we get our 2-part answer. This is a one solution to the system problem because it touches at that one point of intersection. On this next one, I wish we had opposites, but we don't. So we can create opposites with the x's or with the y's. It's up to you. So here, oh, I'm sorry, we do have opposites in this one. Just kidding. So since these two are opposites, the 4 and the -4 cross out. And we can just combine the other ones over here. So -2y minus y, remember there's an invisible 1 there, is -3y. 8 minus 8 is 0. And it is okay to get 0. Don't let that freak you out. So then we go plug this into either of the two equations. That zeroes out and we get -4x is equal to 8 and x equals -2. Again, you can have a 0. That just means that this is the point of intersection at the x-intercept of -2, 0. Now in this last one, we do not have opposites. I wish I could have 8 and -8 or 12 and -12. So I need to think, what number could I multiply here to make those opposites? So if I choose 4, 8 and then -8 will cross out. So here I go. make a new row of 4 times everything. And now 8 minus 8 is 0. That zeroes out. 12 minus 12 is 0. That zeroes out. And 10 minus 8 is 2. So wait a second. 0 equals 2. When is that true? That is never true. So there is no solution. So how is that possible? How can we get no solution to a system again? Well, that means it's 2 parallel lines that never touch. And that's your quick review on elimination. This next page of the attachment is more practice on elimination method that is not required. And then we finished off with doing this section. So the solution to a system of linear inequalities now, we have less thans and greater thans, is the shaded feasible region. So when we go graph these this time, I graphed this one in class and then you graphed this one on your own. We're looking for graphing and then shading one inequality, graphing and then shading the other, and seeing where the 2 shadings touch. So to get this one ready, 4x minus 3y, I need to move the x's over and then divide by a negative. When I divide an inequality by a negative, my sign is going to flip. So right here, this less than becomes a greater than. First thing I'm thinking is when I go graph this, this is going to be a dashed line shaded up. So be careful that you don't just go like into your mode of graphing lines. This is going to be an inequality. It's going to be a dashed line shaded up. Now let's go do this other part. Let's move over the x's. This time I don't have to change the inequality sign. It stays less than or equal because there's no dividing by a negative. And I'm ready to graph these 2. This one is going to be a solid line shaded down. Solid shaded down for that less than or equal. So here I go. Go begin at negative 4, down 1, 2, 3, 4, and then go up 4 over 3. Remember that this is going to be a dashed line and shaded up. All of these points are part of the solution to the 1 inequality. Now I go start at 2 and go down 2 over 3. This one is going to be a solid line and shaded down. Oops. So what is the shaded feasible region? That is the section of the graph that has both the yellow and the green touching. It is this doubly shaded area, and all of the points within this area are examples of solutions. So is 0, 0 a solution? Yes, it's in the double shaded region. I could plug in 0, 0 to this one, and I could plug in 0, 0 to this one, and both of these inequalities would be true. Is 3, 5 a solution? No, it's not in the double shaded region. 3, 5 would work in this one. It would give us a true statement, but it would not work in this one. And it has to be in both. Is 6, 0 a solution? 6, 0 is not a solution because it's not in the shaded region. And 6, 0 would not work in this or this equation. It's not in either shaded region. It would give us false statements if we plugged in 6, 0. So all the points within this double shaded region are solutions to the inequality. Let's go graph the last one. Begin at negative 4. Go up 1 over 2. This first one is going to be dashed and shade up. And last, we're going to be in at 5 and go down 4 over 1, down 4 over 1. This one is going to be solid, shade down. Shading down is everything below this y-intercept of this line. Notice where the yellow touches the green is our double shaded feasible region. It's the overlapped area, this part right here. All of the points within this are the solution to my system.